engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists, the show that brings you the latest breakthroughs in science, technology and medicine with me, Chris Smith. And the attractive topic of magnetism is going under our spotlight this week, including how scientists are using magnetic bacteria to fight cancer and the pioneering project to clean up the hundreds of thousands of bits of space junk we've dumped in orbit.
The Naked Scientists podcast is powered by ukfast.co.uk.
It's The Naked Scientists with me, Chris Smith, and with James Titko. We found ourselves attracted by the topic of magnetism. It's what makes it possible to generate and distribute electricity to our homes or send messages and radio broadcasts like this one over the airwaves. It underpins our ability to see inside the body with technologies like MRI scanners. And thanks to the fact there's a massive magnetic field surrounding our planet, much of the radiation onslaught from space that would otherwise hit us is fended off, and that keeps the planet habitable. Now, that planetary magnetic field also provides us and animals with ways to navigate, and there are even bacteria that can sense the Earth's magnetism and use it to guide their movements. Scientists are in fact now trying to use those microbes to combat cancer, as we'll hear later on.
And that's what we're going to talk about this week. How magnets work, how we've embraced and sought to understand them over human history. We'll see how we're using them to unlock the planet's past, guide therapeutic bacteria into tumours, and even clean up space junk.
Well, with us to start the metaphorical magnetic ball rolling is physicist Michael Coe. He's at Trinity College Dublin and he's devoted his career to the study of magnetism and magnetic materials as well as their history. So, we have to answer the fundamental question first, if you can, Mike, and that is, what is a magnet?
That's a great layman's question. When one of the great theoretical physicists of the last century, Richard Feynman, was asked why magnets attract, he struggled to respond. What he said boiled down to, we would need to have a common language gained by studying physics for a few years. It's really best to accept that they just do and go on from there. In fact, many young people, including the young Albert Einstein, was amazed to discover that you can make a magnet move by just waving another one nearby without them even touching. We just become familiar with magnetic fields and continued from there.
I think Richard Feynman also said science is like sex, but both have practical results. That's not why we do it, though. When did people first become familiar with the idea that this thing you can't explain was a phenomenon, was a real thing, that was there, it was an entity, and that we could see it in action?
I didn't say I couldn't explain it. I said I couldn't explain it in simple layman's terms. But the answer to your question is long, long ago. Because we can find natural magnets, which are rocks called lodestones, that are rich in iron oxide, that have been magnetized, believe it or not, by the enormous electrical current in a lightning strike. They attract and repel each other, and they strongly attract metallic iron. So it was maybe about the beginning of the Iron Age.
So that's how lodestone works. It's nothing to do with the planet's magnetic field. They'd already been magnetized by lightning, and then they interact with the Earth's magnetic field.
That's correct.
And when would people have realised that, because it's a bit of an intuitive leap to go from you dangle a piece of rock up in the air and realise that it always points the same way. When would they have begun to realise this was a useful thing?
Apart from playthings, the first good use of them was made by the Chinese over 2,000 years ago. What they did was they carved a lodestone into the shape of a spoon that you sometimes see in Chinese restaurants. They placed it on a polished surface, and lo and behold, the handle turned to point south. Their application was geomancy, or feng shui, and it was only about 1,000 years later that people realized the effect with a suspended iron needle, or a floating fish, could enable navigation far from land across the trackless ocean. It was the invention of the compass that was the first time that magnetism really changed the world. It was the first magnetic revolution. It led to the great voyages of discovery in the 15th century, when the Chinese admiral Zheng He discovered Africa in 1415, and Christopher Columbus discovered America in 1492.
It's amazing to think that feng shui predates navigation, isn't it? But what about the next intuitive leap, which is that magnetism and electricity are tightly bound together? How did that come to be?
Well, the similarities were really quite striking, But people for years and years were trying to pin down the link, and nobody succeeded until Hans Christian Ørsted, who loved to give public lectures in Denmark, was repeating his demonstration that there was no connection using a long copper wire and lots of tiny compasses. But then in 1820, somebody had already connected the other end of the wire when he connected it to the voltaic pile. And when the current flowed, the magnets began to swing perpendicular to the current. It was that spark that ignited the electromagnetic revolution. Within weeks, the information reached Paris, where Ampere and Arago showed that if you wound the current into a coil, it behaved just like a magnet. And a few weeks later, the news reached London, and Michael Faraday makes the first rudimentary electric motor. The electromagnetic revolution spreads like wildfire.
Goodness. And what about the question of radio, though? Because radio is also electromagnetic radiation. How was the connection made between electricity, magnetism, and then transmitting invisible waves and information that way?
Well, that was really thanks to Maxwell, who developed a unified theory of electricity, magnetism, and light, where the electric and magnetic fields are perpendicular, based on the ideas of Faraday. But the point is that radio is an alternating wave where we have electric and magnetic fields perpendicular. Light, radio, microwaves, they all propagate at the speed of light. We got motors, dynamos, electrical distribution networks, banishing the tyranny of day and night, banishing candles, banishing horses from the streets. And in the 19th century, really the world was utterly, utterly changed.
So there you go, from Feng Shui right through to how we now have electric cars ploughing a furrow along our streets. Thanks very much. That's Michael Curry from Trinity College, Dublin. James.
What an absolute fountain of knowledge Michael was. Now, we all have Earth's magnetic field to thank for the fact that we're all here at all. Without it, we'd have been zapped by space radiation. But our magnetic field can also help us to piece back together the history of how the planet and life as we know it evolved here, because it can help us to reconstruct what the planet was like in the past since it formed about 4.5 billion years ago.
Now, a century ago, Alfred Wegener proposed the theory of continental drift. Many people were unconvinced at the time, but as time went on, more and more evidence began to emerge that proved that he was right. The Earth's surface is formed from tectonic plates, and they're constantly moving and jockeying for position, and they take the continents with them.
The clues to validate Wegener's theory were found in the form of magnetic signatures imprinted into these rocks from the Earth's field as they formed billions of years ago. And from these signatures, geologists like Harvard's Alec Brenner and Roger Fu can work out the location of the rock when it was forged, allowing them to assess its movements over time as what, as Alec explains, the Earth was like all that time ago.
Earlier, we would have been a very different place than the Earth we live on today. And it's been changing ever since it formed 4.5 billion years ago. And of course, plate tectonics is part of that picture. Earth's surface was probably a magma ocean. It would have been constantly bombarded by giant asteroids left over from the birth of the solar system. But within about 100 million years, that surface would have cooled down. Oceans probably would have formed. Its interior was hotter. Volcanic eruptions were probably also quite a bit hotter. There were still occasionally gigantic asteroid impacts. The only living things would have been bacteria. Our research adds to this picture by looking at what plate tectonics and Earth's magnetic field were doing in the background while all of these changes were happening.
How did we transition out of that vision of the Earth that Alex just described?
So this is the hard part, right? We know that, as Alex said, very soon after initial formation of the Earth, let's say 4.4 billion years ago, we probably had a stable crust. The next part is where it really gets tricky, and we don't have anything close to a consensus. And that is how Earth crust became partitioned, right? And this is something that we only see on Earth, and that forms the core of plate tectonics, right? That we have these two different types of crust that collide with each other, and some are denser and sink into the mantle, and some are lighter and stay on the surface.
This is where we come in. We measure the magnetic signals that are preserved by ancient rocks that tell us how these rocks may have drifted horizontally over the surface. The reason that this works is that to Earth scientists like ourselves, rocks are time capsules that can record and then hang on to information about where, how, and when they formed. And the kind of information we are looking for in rocks is magnetic information. And the idea here is that rocks contain tiny grains of magnetic minerals. These are like hematite and magnetite. And those grains act like little compasses that can be frozen in place where they form. So just like you can use a compass to find your way around on Earth when you're navigating out of doors, you can also use these little mineral compasses preserved inside rocks to look back in time at how those rocks moved around on Earth's surface. And the place we went to look for these rocks is in the desert of Western Australia. It's called the Pilbara Craton. And in our research, we went there and measured the magnetic signals of these little minerals preserved in rocks that are about 3.3, 3.2 billion years old. And what we found was that the Pilbara was drifting pretty quickly over Earth's surface back then. In fact, actually at a similar rate to how fast the New World and Old World are drifting apart due to plate tectonics right now. And not only that, but we actually also stumbled on the signature of what we call an ancient geomagnetic reversal, or basically a flip of Earth's magnetic field. And that's where the north and south poles of Earth's magnetic field exchange places. And this happens pretty often on the modern Earth. And what that means is that the ancient Earth's magnetic field acted a lot like it does today, with a north and a south pole that originate from convection in Earth's core.
No, that is very amazing to think over billions of years, which even in geological terms, I think is right in saying it's a long time, that the movement of tectonic plates has remained so consistent. I wonder if either of you could speak to at what point the surface of the Earth maybe became an environment on which life could be sustained. What were the main criteria that needed to be, I guess, solved from Earth as it was in its state before that?
Well, so you'll get a lot of opinions on this. At the most basic level, right, having a surface that's not, for example, thousands of degrees hot, that probably occurred quite early on. Whether life that evolved and could have sustained itself, right, whether there was all the other conditions on Earth, like a stable temperature, the right elements, that is a much tougher question, a much tougher criterion to achieve. We don't know exactly when that happened, but the evidence shows that probably by about 4 billion years ago, certainly about 3.5 billion years ago, there was life established on Earth.
It doesn't necessarily require, per se, that plate tectonics specifically was going on, or for that matter, a magnetic field. It doesn't necessarily require that those factors are present, but the fact that we can now see that they were present certainly adds to the story. We can see today how plate tectonics and Earth's magnetic field lead to conditions that life can take advantage of. For instance, the magnetic field being present, stabilizing the atmosphere against being bombarded from space by cosmic rays. Or in plate tectonic terms, plate tectonics not only creates the environments that living things can make a living off of, but it also plays a whole bunch of different roles all over the Earth system in stabilizing the climate over billions of years, for instance.
If there is a way that plate tectonics is really vitally important for life, that will probably be through this mechanism of temperature regulation. What's famously called the Walker feedback. This is where extra CO2 in the atmosphere is stored in rocks on the seafloor and then gets subducted or gets tucked away into the mantle over long time scales. Without this ability to ship away the surface CO2 in the form of rock and bury it in the deep earth, it's believed that CO2 would build up in the atmosphere. And of course, CO2 is a greenhouse gas and makes the surface hotter and hotter.
Alec Bremer and Roger Fu doing a 4.5 billion year long planetary post-mortem for us there. You're listening to The Naked Scientists, and this week we are examining the science of magnetism, magnetic materials, and their applications. In a minute, we're going to hear from someone who's taking on the task of trying to clear up the hundreds of thousands of pieces of space junk that now litter our orbit. But first, down to earth, both literally as well as metaphorically, because we're going to hear about some exciting work to use bacteria as a way to kill cancers. The idea is that microbes could be armed with destructive payloads that will kill cancer cells directly and or evoke anti-tumour immune responses at the same time. But that, believe it or not, is the easy bit and is actually century-old science.
Yes, the harder problem is how to get the bugs to the right place, in appreciable numbers that is, in the first place. Simone Scherler has an ingenious solution. She's using bacteria that naturally accumulate iron particles that make them magnetic. In fact, these microbes use these like compasses to guide their movements in the world. She creates rotating magnetic fields that behave like whirlpools to trap the magnetic bugs where she wants them, in the vicinity of cancers, for instance.
So I'm a microroboticist by training, and I'm really interested in developing new techniques for more effective drug delivery, particularly for cancer therapy. So we're basically trying to engineer tiny microrobots that can deliver drugs more effectively to a tumor site. And we take here inspiration by nature and actually work with bacteria and use them as a vehicle to deliver drugs to tumors.
Is there any kind of track record of this? When you say you're inspired by nature, that kind of implies that we know this happens.
This idea goes long back. At the end of the 19th century, the American bone surgeon William Coley, who discovered actually in cancer patients tumor regressions when they also had a bacterial infection. He figured that there seems to be a natural tumor homing of bacteria where they can then also have a therapeutic function, such as that they would recruit immune cells. So this was the first form of immunotherapy. So what William Coley actually did when he saw that connection, he deliberately injected patients with bacteria. And for some patients that actually worked out well, and he saw tumor regression and reported these cases. But for others, they actually experienced a septic shock, which you can also imagine having bacteria in the bloodstream. Because of that, and also the rise of radiation therapy, this idea kind of died down. But right now, we are really experiencing a renaissance of this concept, because we have new tools in synthetic biology where we can take more control over bacteria and engineer them in certain ways.
When you say take more control, what do you have in mind?
Well, there's on the one hand control over how they're recognized by the human body, but on the other hand, there's also control over where they go. And this is exactly where I can come in with my microrobotics control strategies. I have been working a lot with magnetic fields and magnetic control. If you have magnetically responsive bacteria, you can use magnetic fields to help them better accumulate in tumor tissue.
How do you make a bacterium magnetically sensitive?
Well, it turns out that nature already has a solution for us. There exist innately magnetic bacteria, so-called magnetotactic bacteria. These microorganisms biomineralize iron oxide nanocrystals. So these are tiny magnets that they have inside their bodies that they produce because they take up iron from their environment. And that has evolved because these bacteria actually live in the oceans. They use it to navigate with the Earth magnetic fields.
So these bacteria do use magnetic fields already, and they accumulate the iron in order to do that. So you're saying we use that mechanism to effectively drive the bacteria or other bacteria where we want them to go.
We can override basically the response to the Earth magnetic field and take control over their direction.
I'm surprised that something which is a tiny fraction of a millimetre long with some iron particles inside it can detect the Earth's magnetic field at all and then meaningfully use it. Do we have any idea how they're doing that?
It's really the torque they experience any magnetic material aligns in an external magnetic field. The string of iron oxide nanocrystals is like a compass needle for them. And we see this in also other animals that have the sense of the magnetic field, that is torque that can be perceived for orientation.
How do you envisage creating fields that will guide the microbes in the right sort of way? Because it's one thing for them to be experiencing a field on the scale of a planet and just knowing up and down, for example. When you're trying to guide something in 3 dimensions through complex tissues inside a body environment to a site that might be, say, a tumour, that's a whole different ballgame.
So it's not that we're trying to give a direction, like go left or right. What we do is basically we apply rotational magnetic fields at the tumor site. And these bacteria behave basically like tiny rods or levers that start turning. And when they do this in circulation, in the blood circulation, with these rotational magnetic fields can help them start tumbling along blood vessel walls. And this is a very important or crucial mechanism, as we identified, because it helps them to find gaps between blood vessels to then get out and get into tumor tissue.
I'm with you. So in essence, you use a rotating magnetic field because that almost creates whirlpools. It's like little eddies which the bacteria fall into, and then they roll along. And then if there is a gap that they can crawl through, they're more likely to crawl through it. So if you center that whirlpool on where the tumor is, they're going to slow down and roll around in the tumor preferentially, which means you're going to enhance the delivery.
I think you've put this very well, yes.
Does it work, though? You presumably are not at the stage where you've put this into people yet, so there must be some kind of model system that you're testing this on.
Yes, so we tested this first in a petri dish. So from the blood vessels, the cells, we were growing them just on a membrane, and then we were adding our bacteria on top and starting with these rotational magnetic fields, and then counting how many bacteria could make it through the cell layer. And we could see that this was significantly higher than when we would have no magnetic field. And then we went further and tested this also in animal models and could see that we find a significantly higher enrichment in tumors when we expose them to these rotational magnetic fields.
Sounds counterintuitive, doesn't it, that you would give someone a bacterial infection to treat a cancer, but that seems to be the direction of travel, and let's hope it works. That was Simone Schuller there. She is based at ETH Zurich.
From tiny microbes up to the vastness of space now, and how researchers are seeking to use magnetic fields to grapple with a large and growing problem. That's the hundreds of thousands, in fact, of pieces of discarded junk that now orbit the planet and pose a hazard to our satellites, spacecraft and astronauts.
Now, much of this stuff isn't made from iron or one of the other handful of what we call ferromagnetic materials, so it's not a simple case of just waving a magnet around up there to grab it, because most of the stuff, therefore, isn't going to stick. So instead, the solution that you need is a far more ingenious one. By creating a changing magnetic field, you can induce an electric current to flow in conductive materials, and that in turn produces its own magnetic field that you can then push or pull against. And Jake Abbott is working on the idea at the University of Utah.
Every day, our society keeps putting more stuff into space, and it's all going in basically the same orbit. Many, many tens of thousands of pieces of junk. And it ranges from tiny little specks of dust to huge rocket bodies. And the problem is they don't burn up fast enough. The orbit they're in is fairly stable, so they could be up there for many decades before they will eventually burn up in Earth's atmosphere. And the problem is, with each new piece of debris, you create more risk of collision. And when there's a collision between debris, it has this cascading effect where it creates more debris that flies off in every direction, like bullets. And if we're not careful, we could eventually end up with a permanent ring of debris around our planet. So there's a big effort to figure out how to get this debris to burn up faster than it would naturally.
What amount of this material up in space is non-magnetic?
It's mostly aluminum. And so you have these huge pieces of aluminum that are typically viewed as non-magnetic. If you try and stick a magnet to aluminum, it won't stick to it. And using all the techniques that we've been using to manipulate ferromagnetic metals over the last 15 years, if you attempt to use those methods, nothing will happen. The aluminum object just won't even move.
So what's the solution?
So we sort of have recently come to the realization that there's a well-known old phenomenon known as eddy currents. If you change the magnetic fields rapidly, just during that period where the field is changing, you will generate electricity, electrical currents in any conductive material. So now this is all of the other metals that aren't magnetic. And aluminum ends up being a fairly good conductor. And so when the magnetic field is changing, these eddy currents get generated in the metal. But what we've figured out how to do is use that eddy current generation to do manipulation. In that moment, you generate these circulating eddy currents inside of these metals. They're almost like little mini electromagnets. And those little mini electromagnets react against the same magnetic field you were using to generate them. And so then you generate forces and you generate torques on those little swirling currents. And so now we can rotate things, we can push things and pull things. It is a way for us to literally reach out into space away from us, pull that object into us. So it's something like a tractor beam.
Why do you need this level of precision to remove the pieces of space junk that you're able to achieve with your method? Why can't you just knock them physically to disrupt their course and make them burn up a bit more quickly?
Some of the pieces of space debris are truly junk, what you'd think of as debris. And really what you're trying to do is deorbit them as fast as possible, meaning make them burn up in the Earth's atmosphere. Some of the things are maybe satellites that used to work and they could work again if you could repair them. So the goal is not to deorbit them, but it's to add another 20 years to their life or something. Lots of people have solved the problem of finding an object of interest and synchronizing some robotic satellites orbit with that object. So now you can imagine the robot and the piece of debris in sort of a synchronous orbit where they're not moving relative to each other anymore. And you say, okay, I want to either repair this object or I want to attach something to it that will cause it to deorbit, to slow it down. The problem is that everyone encounters is when you come upon this object that's been circulating around Earth for a long time, it's often tumbling out of control. And there's no way to grab it safely, because if you try and grab it, either you could break your robot and create more debris, or this tumbling object might have antennas sticking off of it or solar cells. And if you try and grab that, you might turn that one piece of debris into lots of pieces of debris. So this problem of I've synchronized myself with this piece of junk, it's tumbling out of control. I want to grab it and manipulate it, maybe using more traditional robotic methods, but I don't know how to grab it safely. So that's where we come in. We're creating a methodology in which we can detumble this object without touching it. So now imagine the robot has two stages. The first stage is our technology, where this object is tumbling out of control, and we use our magnetic fields to get it to stop tumbling. And then once it has stopped tumbling, then more traditional robotic hands reach out and do the manipulation.
And how's it going? Is this at the proof of concept stage? Is it being developed further? What's the status?
Yeah, well, I mean, we have demos in our paper. We have videos, so you can see us pulling on things. It's over relatively short distances. I've paired with a company called Rogue Space Systems, and we are trying to develop this technology to a point where it could be put in space in the very near future. We've actually had funding from the US Space Force to work on this.
Jake Abbott there on his vision for a real-life working magnetic tractor beam to help us clean up space.
And that, I'm afraid, is where we're going to have to leave it. But I promised you an attractive half hour, and I think that's what it was, wasn't it? Join us at the same time next week, of course, for a dive into the deep sea. We're going to look at the subject of oceanography. We'll take a deluxe tour of the £200 million research vessel that is RRS David Attenborough. And we've put one of our team, Will Tingle, aboard to find out how this flagship operates. And we'll also talk to those at the front line of oceanographic research to see how their work influences the future of navigation and the climate. That's coming up. The Naked Scientist comes to you from the Institute of Continuing Education at the University of Cambridge. It's supported by Rolls-Royce. I'm Chris Smith. Thanks for listening, and until next time, goodbye.